Did you ever wonder what the difference between the natural and artificial sweeteners are? Before you take another drink of that beverage, let's learn about the functional groups that make up these molecules. Hey there, ninjas. Functional groups are extremely important in organic chemistry. By labeling a functional group with a functional group name, that name tells chemists all they need to know about the reactivity of that particular molecule. Telling the chemist a name of a functional group gives that chemist a lot of information about the kinds of reactions that molecule can do. There are a lot of functional groups in organic chemistry. You don't need to know them all, and we're not going to go over all of them in this video. Instead, we're going to go over the basic Ninja Level 1 and 2 functional groups that you need to know in order to make it through organic chemistry. Let's start with what is a functional group. A functional group is a collection of atoms within a molecule that have a particular function. It's a group of atoms that are all bonded together that have a certain chemical personality. A certain functional group can do certain kinds of reactions that another different functional group may not be able to. I like to think of functional groups like rooms in a house. A house is made up of many different rooms all connected together. Each room in a house has a different function. The house is like the molecule and the rooms are like the functional group. But I'm going to take this analogy one level deeper and help you avoid some of the most common functional group mistakes in organic chemistry. Just like a house may have different rooms, a room may have different appliances within that room. Your kitchen has a sink and a refrigerator and an oven. In the same way, a molecule may have different functional groups, and the functional group may have different fragments within that functional group. A functional group can be made up of one or more fragments all bonded together. And here's the thing that always trips up students. Different functional groups in organic chemistry may have the same fragments within them, but they're still different functional groups. To go back to our house analogy, your kitchen has a sink and your bathroom has a sink. Both rooms have the same appliance, but they have completely different functions. You wouldn't wash your dishes in the bathroom sink, and you're probably not brushing your teeth in the kitchen sink. Same appliances, different rooms, different functions. Some of the functional groups we're about to see have the same fragments, but they're parts of different functional groups with different functions. The first functional group I'm going to show you actually really isn't a functional group. An alkane is a hydrocarbon that lacks any functional group. As such, it's kind of a foundation without a house. The fragment that is part of an alkane is called an alkyl fragment, or an alkyl group. The functional group is alkane, the fragment is alkyl group. The name of the room in the house is an alkane. The name of the appliance within the alkane room is called the alkyl group. I also kind of like to think of it as noun and adjective form. The noun form of this functional group is alkane. This is an alkane. The adjective form of this functional group is an alkyl group. This functional group contains an alkyl group. Although again, this is kind of the lack of a functional group. If your instructor asks you to identify certain functional groups in a molecule, alkane is not one of the ones you will identify. Otherwise, every molecule would have 15 or 16 different alkyl fragments. So let's look at some functional groups that you can identify. We're going to be making a pretty big grid of functional groups here, and this will be the bottom left cell. I would recommend turning your paper long ways and make this the bottom left corner of your page so we can build out this grid of functional groups. The next functional group is an alkene. An alkene has a carbon-carbon double bond as its functional group. The name of the fragment within the alkene is a vinyl group. The name of the room is alkene. The name of the appliance within the alkene room is the vinyl group. The noun form of the functional group is alkene. The adjective form of the functional group is a vinyl group. The functional group that contains a carbon-carbon triple bond is called an alkyne. And the name of the fragment within the alkyne functional group is a propargyl group. The noun form is alkyne. The adjective form is propargyl. The name of the room in the house is an alkyne. The name of the functional group within the alkyne room is the propargyl group. For all of these molecules, I have CH3 groups at either end. That's not important. This molecule could be as big and as ridiculous looking as we need it to be. What we want to focus on is just the alkyne fragment, just the alkene fragment. The next functional group I'm going to show you, I'm not going to put in our grid, but you still need to be able to recognize this functional group, and that is an aromatic ring. There are actually a whole bunch of molecules that can be classified as aromatic rings. I have a video on aromaticity in the description down below. This ring you've likely seen before. It is a benzene ring. It is a kind of aromatic ring. The name of the fragment within this benzene ring is the phenyl group. It doesn't quite fit in our nice grid, so I'm not going to include it as part of the grid, but you do need to be able to recognize aromatic rings. Next, I want to fill out this row of the grid that we're starting to make. And the first functional group I want to tell you about is a haloalkane. A haloalkane, or sometimes called an alkyl halide, is a regular alkyl carbon chain with a halogen attached through a single bond. That fragment with the halogen is called a halide. The noun form of this functional group is haloalkane, and the adjective form of this fragment is a halide. One thing you do need to keep in mind with the haloalkanes is that X here is just a placeholder for a specific halogen, either a fluorine atom or a chlorine atom or a bromine atom or an iodine atom. So in the wild, when you see a functional group, it won't have X written here, it'll have a specific atom written here, and we'll update the name to include that specific atom. If X here were a bromine, we would call it a bromoalkane, and the name of the fragment would be a bromide. Next, we have one of the most common functional groups in organic chemistry, and that is the alcohol. The alcohol is an OH group attached to a single carbon. That OH group fragment is called a hydroxyl fragment. An alcohol consists of a single hydroxyl group connected to a single carbon. Be careful with this hydroxyl group. It's going to trip us up later on. For now, we need to know that when a single hydroxyl group is connected to a carbon chain, that is the alcohol functional group. The next functional group is an amine. The amine group has an amino fragment attached to a single carbon. Now, I have to tell you, amines can be a little bit tricky. The amino fragment attached to the carbon chain can either be a nitrogen with two hydrogens attached, a nitrogen with one hydrogen attached and another alkyl fragment, or a nitrogen with two different alkyl fragments attached. We call all of these amines. Though the amino group can change slightly, they're all amino groups attached to a carbon chain. The next functional group is also historically confusing for students, and that is the ether functional group. An ether is an oxygen bonded to two different carbon chains. It doesn't matter what those carbon chains are. They can be a 3-carbon chain, a 1-carbon chain, something with an aromatic ring. It doesn't really matter. An ether is an oxygen sandwiched between two carbon chains. That fragment, consisting of the oxygen and the other alkyl chain, is called an alkoxy fragment. The noun form is ether. The adjective form is an alkoxy fragment. The room is the ether. The appliance is the alkoxy group. Notice the structural similarities between the ether group and the alcohol group. The alcohol group is a carbon chain with a hydroxy group attached, the OH group. The ether is a carbon chain with an alkoxy group attached, an OR group. Also related to alcohols is a thiol, sometimes called a mercaptan. The thiol is very structurally similar to an alcohol, except instead of an OH group, there's an SH group that we call a sulfhydryl group. There is also a thioether group where we have a sulfur with another alkyl group on the other side, but I'm not going to include that in this list. The final functional group in this row is a nitroalkane. A nitroalkane is a carbon chain that has a nitro group attached, a nitrogen double bonded to an oxygen, single bonded to an O-. Notice that the net overall charge of the functional group is still net neutral. That completes this row of this grid. We're going to move on to the next row now. I have a vision for where we're going, a grand unifying theme. That's going to make this video a little bit long, so I'm going to link that second video down below. In the next row, along with the alkyne, we'll start with the ketone. The ketone functional group contains a carbonyl fragment. Carbonyl, not carbonyl. The carbonyl fragment consists of the carbon doubly bonded to the oxygen. Friends, there are lots of functional groups that contain a carbonyl fragment. We haven't really seen that yet, but this gets into exactly what I was talking about with the different appliances. We're going to start to see a variety of functional groups that have this carbonyl fragment, but they're all going to be different functional groups with completely different functions and completely different reactivities. Now, those reactivities are all going to be related because they all contain the carbonyl fragment. Just like every room that contains a sink is related, the sinks do the same sink things, but the overall function of the room, the overall function of the functional group is going to be different for all of these different carbonyl-containing functional groups. For our purposes, what sets the carbonyl functional groups aside is what's on either side of the carbonyl carbon. For a ketone, there's an alkyl chain on each side of the carbonyl carbon. Contrast that with our next functional group, the aldehyde. The aldehyde has an alkyl group on one side and a hydrogen atom on the other side. These are structurally similar but distinct. The presence of the hydrogen versus the alkyl group makes one an aldehyde and the other a ketone, but they both contain carbonyls. And they're both contained in this same row of the grid, and I'll explain why that's important to you in that other video. The next functional group in this row does not have a carbonyl, and it is an epoxide. The epoxide is a little triangle functional group, a 3-atom ring where one of those atoms happens to be an oxygen. The name of the fragment within the epoxide functional group is an epoxy group. You may have heard of epoxy resins. Well, guess what? Those epoxy resins contain epoxide functional groups. We'll find later on in the course that epoxides are very reactive. The next functional group, heads up, is another historically confusing group. And this functional group is an acetal. If an ether was a carbon chain with one alkoxy group attached, an acetal is a carbon chain with two alkoxy groups attached to the same carbon. And that's important. Both alkoxy groups need to be attached to the same carbon for the functional group to be an acetal. And just like aldehydes and ketones, we now have a second example of two functional groups with the same fragments, two rooms with the same appliance. What makes an ether is one alkoxy group attached to the same carbon. And what makes an acetal is two alkoxy groups attached to the same carbon. They're similar but distinct. We can't call an acetal an ether. It's not an ether, it's an acetal. Telling your chemist friend that your molecule contains an acetal means something completely different than telling your chemist friend that your molecule contains an ether. We can't confuse these functional groups and we can't use the words interchangeably. I'm going to include two bonus functional groups that I'm not going to put in this list, but they're very closely related to acetal. One of them is the hemiacetal. A hemiacetal, hemi, is like half of an acetal. If the full acetal had two alkoxy groups attached to the same carbon, a hemiacetal has one alkoxy group and one hydroxyl group attached to the same carbon. Different appliances connected to the same carbon make a new, unique functional group. It would be inappropriate to call this an alcohol or an ether. It's neither of those things. It's a hemiacetal. Both alcohols and hemiacetals contain a hydroxyl group. Both ethers and hemiacetals contain an alkoxy group, but none of these are interchangeable. And a hemiacetal is its own unique functional group. It happens to be composed of fragments that other functional groups also share. Not a big deal. This happens all the time, but we just need to be very precise with the words that we use, and we need to very precisely label our functional group. The other bonus functional group is a hydrate. Do you see the structural similarities between the hydrate, the hemiacetal, and the full acetal? They all contain two oxygen-containing fragments attached to the same carbon. The hydrate has two hydroxyl groups attached to the same carbon. It is not not the same as an alcohol. The two hydroxyl groups connected to the same carbon makes this functional group a hydrate. The next functional group in our list is an imine. The imine is characterized by the amino group as the fragment in its functional group. The amino fragment is very structurally similar to the carbonyl fragment with the nitrogen in place of the oxygen. And just like we saw before with the amine, the imine can have an alkyl group in place of the hydrogen on the double bond. It's not whether this is a hydrogen or an alkyl group that's important, it's the carbon-nitrogen double bond connected to the carbon chain that makes this an imine. The last group in this list is going to be the enamine. Vowel sounds are very important in functional groups. We use a long E here. This is an enamine, as in it looks like it has an alkene and an amine attached to the same carbon. An enamine. Other places where vowel sounds are important is differentiating between an alkane, an alkene, and an alkyne. We have to make sure we get those vowel sounds correct to tell the listener which functional group we're talking about. Also with ether, I hear a lot of students try and say ether. No, it's a long E. We say ether. Long E, ether. The enamine functional group has an amino fragment and a vinyl fragment connected to the same carbon. It's very similar in chemistry to the imine group. The next functional group goes up in our next row, and it's a carboxylic acid. Carboxylic acids are another very popular functional group in organic chemistry, and they combine two fragments that we've seen before attached to the same carbon. A carboxylic acid has a carbonyl and a hydroxyl group attached to the same carbon. This is not an alcohol. I so often hear students try and tell me that this is an alcohol attached to the carboxylic acid. It's not. It's a hydroxyl fragment as part of a carboxylic acid. Both alcohols and carboxylic acids have hydroxyl fragments, but they're completely different functional groups with completely different reactivities. They just both happen to contain a hydroxyl fragment. Yes, I get that's confusing, but these words have a very specific meaning, and it's important to be precise when you're communicating chemistry. We talked before that the way we're going to differentiate our carbonyl function groups is what's on either side of the carbonyl. For the carboxylic acid, we have an alkyl chain and a hydroxyl fragment on either side of the carbonyl. The next functional group is the ester. It is a carbonyl-containing functional group with an alkyl group on one side and an alkoxy group on the other side. Just like alcohols and ethers were related whether or not they had a hydrogen or an alkyl group, carboxylic acids and esters are related by whether or not the oxygen has an alkyl group attached. The two most commonly confused functional groups I hear from students is confusing ester and ether. They sound very similar. They both have alkoxy groups. I totally get it, but we do need to know which one is which. Next is an amide. Now, this one has a bit of regional variation in how you say this functional group. I say amide, but I've also heard people say amide or even amide. Which one is correct? Whichever one the speaker is saying. I'm sure they will defend quite passionately why their pronunciation is correct. In any rate, the amide functional group is a carbonyl with an alkyl chain on one side and an amino group on the other side. And you guessed it, it doesn't matter if the nitrogen has two hydrogens or one alkyl group and one hydrogen or two alkyl groups attached. These are all kinds of amide. The next functional group in this row of our grid is the acid halide. The acid halide is a lot like the carboxylic acid, except instead of having a hydroxyl group, we have a halide group. And acid halide is a carbonyl with an alkyl group on one side and a halide group on the other side. Just like the haloalkane in the real world, an acid halide will have a particular halogen attached to the carbonyl. For our purposes in organic chemistry, it's almost always a chlorine, so we will almost always encounter an acid chloride as a functional group. Next is an anhydride. We don't see anhydrides all that often in organic chemistry, but when you do, you'll know that it's a carbonyl with an alkyl group on one side and a carboxylate on the other side. The last functional group we're going to talk about in this list is a nitrile. The nitrile is a functional group with a carbon-nitrogen triple bond, and that fragment of the functional group we call a cyano group. The noun form is nitrile, the adjective form is cyano. The name of the functional group is nitrile. The name of the fragment within the functional group is a cyano fragment. The name of the room in the house is the nitrile, and the appliance in that room is the cyano group. So there you have it. This is our master list of functional groups you need to know for organic chemistry. How many of these do you need to memorize? All of them. Remember, this is actually just a subset of a huge number of functional groups in organic chemistry. These are the important ones we're going to see most often in this course, the ones about whom we're going to learn how their chemistry works. These are the functional groups we'll learn how to make with organic chemistry reactions and how to use them as starting materials to do chemistry reactions. And you have to have these functional groups down cold. You need to be able to look at a molecule and know that's a ketone, that's an ether, that's an alcohol, there's an alkene. You need to be able to point out these functional groups with rapid succession. So flashcards are probably in your future. Just keep in mind as you're making those flashcards that the molecule doesn't have to look like this. The ketone could be anywhere in the molecule, could be upside down on the left side, the right side, doesn't really matter. The functional group is part of the entire molecule, and we need to identify that functional group. Like I said, I have a very good reason why I made this grid the way I did. So again, I'll link you down to the video in the description for why this grid is really useful for organizing your organic chemistry reactions and learning that functional group reactivity that you need to know. But for now, let's go back to that drink on your desk. Take a look at the ingredients. Does your drink contain one of these sweeteners? Now that you can see the structure of these sweeteners, we can look at what functional groups are contained within these sweeteners. At the top of the glucose chain is an aldehyde. This aldehyde is written in condensed formula notation notation. If you need help with condensed formula notation, I have a video about that I'll link to down below. Glucose also contains a lot of alcohols. There are 5 hydroxy groups in glucose as part of 5 separate alcohols in this molecule. This is part of what I mean that you need to be able to look at these molecules no matter how they're oriented and know which functional groups are present. Aldehyde, alcohol, all the ones down the line. What about steviol? Take a second, pause the video, see if you can identify the functional groups in steviol. At the top, steviol also contains another alcohol. Next to that alcohol, we have an alkene. And in the bottom corner, a carboxylic acid. It has several rings in the middle. Those are not aromatic rings. They don't have the double bonds. They are alkyl fragments. But again, we're not going to label alkyl fragments, otherwise we'd be labeling them all over the place. Take a second, pause the video, see if you can identify the functional groups in aspartame. On the left side, aspartame also contains a carboxylic acid. Be careful with these nitrogens. Make sure you get the right functional groups in the right place. First in line, we have an amine. This NH2 amino fragment is the only thing bonded to this carbon. It is the only fragment on that carbon. This is an amine. Next to the amine, we have an amide. Here, we have the amino group and the carbonyl both connected to the same carbon. That makes this an amide, and the green one an amine. In the top right, we have an aromatic ring, and finishing out the molecule, we have an ester. Notice I've written the alkoxy group as an OCH3 group. It's still an oxygen with an alkyl group attached, which is also attached to a carbonyl. The alkoxy group and the carbonyl together make this an ester. Final structure, pause the video, see if you can identify the functional groups in sucralose. Sucralose has 5 hydroxy groups as part of 5 different alcohols in the molecule. You would label these as alcohols. It also has 3 haloalkanes, but specifically these are chlorines, so you should label this as a chloroalkane. And finally, this group contains 2 overlapping acetals. That one was tricky. Did you find that one? Did you want to call them ethers at first? It's subtle, but there are 2 alkoxy groups attached to the same carbon, both on the left and on the right. That makes these 2 separate acetals. Which functional group is your favorite? Let me know in the comments below. You got this, ninjas.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.